So we're going to be considering
Oh,
how,
oh, sorry, I was muted.
yeah. So
Oh,
we're going to basically determine how to determine the velocity of a wave on a string, right?
yeah.
And just think about, before we actually think about the formula and so forth, let's consider what we said earlier, right? We've got a frequency must equal V over 2L, right?
Yeah.
Now, just from your general sort of experience, do you know sort of string instruments?
Yes.
Right. How do you make the note sound higher on a string instrument?
So the string vibrates harder.
Well, yes, but it does. But I mean, just when you play a string instrument, how do you make it go higher in pitch?
Um, there are like, oh, okay. So you hold on some parts of the string.
Right. You can place your finger, on the string. Now the question is, while we're on this topic, if when you move your finger, how do you make the note sound higher when you move your finger? Do you move it closer or further away, kind of thing?
Closer.
So the closer the finger is, to the, let's say the bow or the pluck, then the higher the note.
Yeah.
So that's one way. What's another way that we could make the note sound sort of higher? Just think in terms of the instruments, right? You've got your string. Now, let's say your string is out of tune. How do you make it higher in pitch when you tune the string?
Oh, so you make it more tight.
Right. So the tighter the string, the higher the sound. And if you compare your strings between the ones that sound high and the ones that sound low, do you notice any difference between the strings themselves? Like the ones that are low pitched versus the ones that are high pitched, do you notice any sort of difference in the strings? Do they all look the same?
Oh no.
So the ones
So
that
the
are
low pitch will be thicker.
right. So basically, if we're talking about to make the sound higher, then the sort of thinner strings sound higher. Does that make sense?
Yes.
Great. And we're basically going to be trying to explain some of these in terms of the velocity and the fundamental frequencies that we've been talking about earlier. So we know that, for higher pitched, frequency is higher. We know that. Now, it does relate to the velocity. And here's the thing. We won't really need to go and derive this formula, but I will give it to you and you will need to know this. But the speed of a wave in a string is equal to the square root of t divided by m over L. So v here is the velocity of the wave in meters per second. Now, your t here is tension in newtons. And so that basically explains why, that's basically how tight you make this string, right?
Yeah.
Your m here is going to be the mass of the string, and that will be in kilograms. Now, m is mass, and L here is the length of the string, which is in meters. And m is mass and L is string, but I think it might be easier to think of the ratio m over L in the denominator. This is the mass per unit length. So it's basically like saying, for every meter of string, how massive is it? How much mass is there? And, if you're making it of some material that's very, very heavy, then it won't vibrate much. Whereas if you, so the material itself will affect that, right? The type of material that makes up the string. If you've got a material that's very, very heavy, it won't vibrate much. If it's got a material that's going to, you know, be very light, it'll vibrate a bit more. But if you use the same material, let's assume we don't change the material type and it's all the same material now, then the M over L is basically saying how much mass there is per unit length. But if the density is the same, because you've got the same material, then we're essentially basically saying how much of the stuff you've got in the same length, which can basically be affected by the thickness. So this can be affected by, for example, the material type, because that will affect the material density, and it will basically be affected by the thickness or the cross-section area, if you like. Of your string. Now, if we're assuming our strings are all kind of cylindrical, then basically it just depends on how thick the string is. And so, looking at this formula, the key things to probably take away here are, as tension increases, velocity will increase. And vice versa, right? Tension goes down, velocity will go down. Now, if nothing else changes, as M goes up, that means M over L goes up, which means the denominator goes up, which means the thing inside the square root goes down, which means velocity goes down. Now, if I increase the length, again, the denominator goes down. If the denominator goes down, that means this thing goes up. And if this goes up, that means the square root of, so for L, it's going to increase, which means the denominator decreases. If the denominator decreases, that means this whole thing increases, which means the velocity will go up.
Yeah.
Okay. And that's basically how it's going to affect things. Now, but more importantly, I think we should sort of combine these. It's probably better to combine these to think of it as what happens to M over L. If M over L goes up, so basically if you make the string thicker, if M over L goes up, because very rarely are you going to keep the mass the same and make the length increase, right? Well, you could do it by stretching out the string, but if M over L goes up, so basically if it goes thicker, then you'll notice that if it goes thicker, then velocity will go down. Okay. And if you look at what we did before, where F equals V over L, so if V goes up, then that means frequency will go up. If V goes down, that means frequency will go down. And that is how we can explain that as we make the string tighter, because through this formula, as we make the string tighter, tension goes up, which therefore means the velocity of the wave goes up. Then by this formula, the frequencies would go up. And that is why the tighter the string, the higher the sound. Yeah. On the other hand, the thinner strings are when this goes down. If M over L goes down, that means velocity will go up because this goes down, so this is bigger, which means V will be bigger, which means the frequency will be bigger. And that's how we explain those examples. Now, the last thing we kind of need to explain is why, if we place a finger on the string, then it will be higher the note. And this basically comes down to the sort of situation that we've talked about here. So we've said before that your fundamental frequency is A and B. And because of the way it draws out, you'll end up with a situation where you've got your lambda equals L over, 2L, and your fundamental frequency is going to be V over 2L, and all your other frequencies are multiples of this fundamental frequency. And so here's the thing. If you end up putting your finger somewhere on the string like here, so we'll call that F, right? And let's say, you have your bow here, which means this end of the string is vibrating, right?
Yeah.
Now the thing is, if you put your finger here, can this part move?
Can which part?
If I put my finger here, then can this part of the string move?
No.
No. So if we put a finger at capital F, this now makes F a node. So in other words, instead of the node being where it was at A and B, this node has been shifted to here, which now means your new wave so therefore the old wave can no longer exist. Therefore, the new wave has a new fundamental frequency. And by shortening the length, you've essentially shortened the length, which is higher, because L basically decreased. So in other words, placing your finger essentially is thought of as reduction in string length. You've basically reduced the length of your string, how much it can vibrate. And that is how it works in strings.
Yeah.
So how do standing waves work in pipes?